A very good morning, all of you. I hope everybody is fine. Let's continue with our lecture. In our previous class, we discussed about Ethernet frame structure, and we were discussing about hubs. Now, hubs were the simplest way to, broadcast. So when we say it has a single collision domain, it means that if we have, let me just draw a picture here. So if we have one segment here, another here, and this is the backbone, this one has some more, this one has more, and this one has more. So something like that. It means that a single collision domain means if A here has to send to B here, all the nodes that are around here, whether it's this or whether it's this, all of them will be receiving this packet because this node will broadcast it and this is connected to it. It will go to it, it will broadcast it and it will go. So even if A is sending to B or A is sending to C I have mentioned here, it will be broadcasted. So this is what we know as a single collision domain. Don't press annotate, it will get prepared. Let's check if okay, so somebody pressed annotate, so it's disappeared. Better not do that. So the problem with the hubs that we saw here was that the packet that was broadcasted, it would spread across. So that's what we call as single collision domain. And hubs do not buffer frames. Hubs operate in bits rather than on frames, so we'll consider them as physical layer devices. Keep that in mind as well. Also, they are nothing more than repeaters. I'll just add a few more points here. So they do not buffer frames. They are physical layer devices as well as they are just repeaters. Okay. So there are problems with this having hubs. We cannot have a bigger network because the big collision domain and there will be a lot of collisions with that regard. Also distance between the two hosts, it will be limited, and maximum levels how many we can have, that is all limited by the design of hub. We can't have many tiers of layers. And compared to this, we move to the next one, that is bridges. Bridges are known as layer 2 devices, work on frames. Okay, so they know about the MAC address. They do filtering and forwarding, which we discussed in our previous class. Now to understand more about this and the work that the router does, let's go to this example. Let's see this. Bridge, after actual bridges come switches. I'll come to that as well. But switches are mostly advanced bridges. with more number of ports. I'll take them in a little while, but first let's see this picture. This we discussed in the previous one, how MAC address, how it works, how it looks like. Let me see this one. So an important thing to understand here is that this here, the one which I just now made a green round, this is the sender, and the other green one which here, this is the receiver. Okay. So in between we have nodes. One is a switch here, another is a router here. Fine. Now when the sender sends it, okay, the sender sends it from, let's say, Facebook Messenger here. So we have here FB here, and it sends to the Facebook Messenger of the destination here. So FB Messenger gives the data to the application layer, which forwards it through various layers, which is here. And we have at network a packet, you can call it datagram here. Then we have a frame at data link layer, then bits, and then it's physically sent to a layer 2 device, which can be a bridge, or it can be a what you call switch. Now if you say there was a hub as well, let me just add a hub as well here to understand that. So let's say there is a hub also. So from here it moves. Somebody again press. Don't press annotate. Ramanan, just check it out how I can log this annotation so that others can't press it. Okay. So if it goes down from here, it goes to the hub here. Hub has only one layer of networking, that is the physical layer. So we expect it to go like this. Means hub would understand it as bits and then pass it on to a switch. Within the switch, it has two layers. It goes to the physical layer up to the data layer. That is it's the frame destination and so on. Beyond it, what is the IP address? What are the higher layer protocols? For it, it's just all data. It cannot understand it because it's only layer 2 device. Keep that in mind. Then you pass it on. It goes to the router, that is here. Our router has physical layer, passes on to the data link layer, passes on to the network layer, checks the IP address, the destination and so on, works on it and then sends it back to the destination here. At the destination, you have first physical layer, the link layer, and until it reaches to the destination, that is the Facebook Messenger. So from here, this application to this application, this is how it goes through the devices. Now, few things that you have to keep in mind, that this terminal and this terminal have all of the protocols available here and here. They have the full protocol stacks. Whereas intermediate devices, some have 3, some have 2, and some have only 1, that was the hub. Some protocols are not available in router, some not in switch, and some not in hub. Why? Because they do not have all the layers. Those protocols which are beyond the network layer, above here, transport on, they are known as end-to-end protocols. They are known as end-to-end protocols. Why we call them end-to-end? Because they are mostly available at the ends, at the two sender and the destination. Now, seeing the difference between the switches and the routers that has been mentioned here. Obviously now router has three layers. It works on network layer. It's a network layer device. Switch is a layer 2 device. There are some managed switches which are of layer 3 as well. We'll keep them separately. As of now, let's take them as a layer 2 itself. So switches here would work on frames. They would see destination MAC address, whereas the router, they can see the destination MAC address also, but they can see the IP address as well. Now, the thing is that if we compare a bridge and a router, uh, routers are forward and forward in the sense that the packet is received by the router, it will completely receive the whole packet and then it will forward. Bridge is also a store and forward device. Bridge would also wait for the whole of checks where it is and goes and forward. Compared to this, let's try to see what we have as switches. See switches. So in switches, we have very high performance bridges. The thing that we have here is we have multi-interface bridges known as switches. It's or this is the place where you connect. Switch would be 8 port, switch would be 10 port, and so on. Sorry, typically it's 8, 16, 32, and so on. Switch would have small number of interfaces like 2 or 4, and switch can have dozens. Also, in terms of performance, switches are very high performance device, 100 Mbps, more than that, in fact, 1 Gbps. And most of the switches nowadays work on full duplex mode. Now, my point here is to explain a term which is cut through switching. Let's try to understand what is cut through switching. As compared to routers and so I'll just write it. Router and bridge, we have store and forward. But switch is cut through. What do we mean by this switch is cut through? It means that when a packet arrives at the, let's say this is, let's try to understand this. I hope you will understand. This is a switch. Let's say we have this as a switch. It has several interfaces like this one, and this one, Now, what happens here in cut-through switching is an interesting concept here is that packet is being forwarded from one direction to another. In this case, let's say there is interface 1 and this is interface 2. Okay. Packet starts arriving at the inbound link. Let's say this is the packet. So it would have ones and zeros across within it. If the other link is empty here, that is the outgoing link, okay, then this packet does not need to wait. If there are packets within outgoing link, then this packet will need to wait. That's why we have a concept of buffer here. It's a temporary memory where you can store the packet. What is basically cut-through switching? Cut-through switching says that if the link here is empty, that you can see no transmission is going here, directly bring this packet, okay, and start transmitting. Directly bring the packet. As soon as the packet starts to arrive, start move it across without let packet not wait. So this means that the whole of the packet is, I mean, you don't have to wait for whole of the packet to arrive. Once it starts to see the ones and zeros that are arriving here, it starts to pass on to the link from here to here. This means that the packet does not have to store and forward. So this store is missing, it only forwards it. How does it help? It helps us in having no store and forward delay, SF delay. Okay. This would help us in minimizing the store and forward delay because you are not waiting for whole of the packet and then you transmit. But there are some things that we have to take care here. If there is a packet which is already being transmitted on the other link and a packet comes from inward link here, the switch cannot directly pass it on to the onward link because the link is already busy. In this case, the switch has to go to the buffer here and get saved. Even though packet here switch is a cut-through switch, it cannot pass it directly in the case where the output link is free. If it's not free, it has to go into the buffer and then only from here it would be transmitted onto the output link. So I hope you understand here. Store and forward, you would have to first necessarily wait for the whole of the packet to arrive. Once it is arrived, then only you can transmit it. But in other case, cut through switch, you can directly send it across. Good. You have minimized the store and forward delay at the switch, which was contributing to the overall delay. And how much was that? Store and forward? It was dependent upon the length of packet, right? L by R, where R was the transmission rate. Okay, I hope you understand that. But there's one question here. There is one important aspect of cut-through switching in which The packet cannot do cut through switching until unless that thing is done. What is that? That is the portion of the packet that contains the destination address must arrive first. So if you had a stream of ones and zeros, you would expect that the destination address is in the thing itself. Why? Because the switch has a number of interfaces. Since it would have a number of interfaces, like here, in order to decide where this packet has to go, it should have its destination address. If it has the destination address first, then it would accordingly decide that yes, now I will try to send it across, let's say, to this one link. So to know that it's to be sent on this particular link, address, that is the MAC address of destination, is a must. So keep that in mind. That's why if you go back to previous classes where you see the Ethernet format, you see here, the first part that you see here is preamble. What was preamble? A specific pattern by which you get to know that the packet has started, and with the specific pattern of 101011, you can inform the destination that after this 11, the first thing that you'll be receiving is destination. That's why you can see here destination address is at the beginning, then comes source, and then comes the data and other stuff. So for cut through switching, it is necessary that we should have the destination address arrived first. Thus, packet need not be stored before transmission. So I believe that was the end of it. But one thing, this MPLS, you can discuss about it. One comparison as a table I would like to draw here. Let's do a comparison between hubs, bridges, routers, and Ethernet switches. So we have here hubs, bridges, routers, and switches or Ethernet switches. First, we do comparison based on traffic isolation. What is traffic isolation? Can you separate one domain from another domain? If two departments connected, can you separate them? That is what we mean by traffic domain here, traffic isolation. Hubs, they cannot isolate it. Like we mentioned, they have a single collision domain. Rest, all of them can separate the traffic. So if you have two departments connected by a hub, or let's say two hostel blocks connected by a hub, the traffic from one block would go to another block. But other than hubs, all other devices can separate it. Plug and play. You just plug it in and it starts to work. Hubs, yes, no configuration. Bridges, yes, it can do. No router, you need to configure router, so on. Typically, basic unmanaged switches are plug and play. But if you are managed, then you would need to do some configuration. Then we have optimal routing. No routing done by hubs here. No routing done by bridges. Yes, routers main function is routing. They can do it. And switches also no option. And then the last point that we just now discussed, cut through. Okay. We know here cut through routers. We had a no. Another thing, bridges, we had a no. And Ethernet switches, yes, we have cut through switching. But how about hubs? If you remember, if you remember hubs, I mentioned in the hub, if you remember in the hub, I mentioned in the hub that when we have to transmit a bit, the physical layer devices, they are nothing more than a repeaters. It simply broadcasts the bit on all other interfaces. It does not store anything. I mentioned that it does not store. It doesn't have a storage buffer where it can store. It simply goes on forwarding it. And it broadcasts to all. Thus, hubs are simply cut through. So we'll say yes here as well. I hope you understand the concept here. Uh, Anybody has any questions? I think this was the end of the data link layer. So we have covered layer 2 as well. Now today we will go to the next layer, that is the network layer, one of the important layers of OSI. And before I start that, Ramanand, when was the last day of the assignment? So as of now, how many assignments have we sent? I mean, I have given you 2 assignments and 1 for the lab. And you have submitted for 1 as of now. Okay, okay. So let's fix a due date for second assignment. Yes, Sunday. That would be one more. Oh, okay, fine. Okay, fine. Sunday, that would be 24th. Okay, in between this week, I'll give you one more, since I believe, there will be a lot of assignments you will be getting, because 50% is based on assignment quizzes and so on. After we finish network layer, we can try to have an online quiz. Okay, that would be second thing. As of now, I believe we don't have to take the lab. As per the notice, there was no mention about lab, but still, I would want you to try the riverbed model, because it's very good. Software for simulations, but you can do that separately. We have the meeting today afternoon, and we'll see there also what we'll discuss regarding how assignments and other things are to be given. Okay. All right, let's continue. Let's continue with the next one, that is the network layer. One of the important layers in the the OSI model, that is the network layer. It is the layer 3 if we go from bottom to up. So we expect that in network layer, uh, some data is given by the higher layer, that's the transport layer. It works on it and then passes on to the data link layer. As of now, we are aware of the functions of what the data link layer does, as well as the functions of what the physical layer does. To begin with, first thing that we have to understand, network layer, where will it be? Just now we saw a picture in which there were two devices which mentioned network layer. Both of them had both of them had this network layer protocol. The first one that we saw was the end-to-end systems. One was the sender, another one was the receiver. Let me start a presentation. All right. So this is our network layer. There are two parts of it, the data plane and the control plane. This is overview of it. And the chapter goals here. So network layer transports, packets from one end to another end. It actually delivers the packet. You can see here, network layer marked in red is present in the two end systems. So we say if we virtually see it, virtually you can say that we have a link between this network layer and this network layer. The line which I have drawn, let's see, maybe it's not clear. I would just use a better tool. This is how it looks like. Fine. But actually, these do not directly communicate. This is a virtual link between network layer of the sender and the network layer of destination. The actual path that we have, I will mention the actual path in pink. This is the actual path, and then it reaches the network layer. So pink is the actual path and green one is the virtual path. So we say two network layer are communicating with each other, but actually network layer passes on to the data link layer, data link to the physical layer, then to the physical link through the routers, it goes up. Another thing that you see in this figure is actually the presence of routers. What I mean the presence of routers, you do not see any other device other than routers here. There are no switches, there are no hubs, okay, there are no bridges in between. Why? Because they cannot understand the network layer. They do not have that part of it. They are either layer 2 or layer 1 devices. That's why the network layer part of it is in all other systems that have been mentioned here, whether they are routers, okay, or whether they are like bigger base stations, or whether they are the end systems like servers and desktops. You can see here network. So we can say in short that network layer protocols are available in every host. That is the sender and the receiver. That's the server here and the laptop in the figure. And the routers that are in between the sender and the receiver. So data came from higher level, went through this path, network layer, passed on through the routers. Each router had its own network link, took the data up to the network link, like you can see here. See the flow, how it works. And then reaches the destination, goes up. So the network layer functions that we generally see here, three important network layer functions. The first function is path determination. What is path determination? Path determination says that network layer must determine the route or the path from source to destination. It is hit work. How it would use an algorithm. What algorithm it is? It's a routing algorithm which finds out the destination. We'll discuss about routing algorithms. We'll see what they are, like link state routing, distance vector, and so on. That is the first thing that it has to do. Find the path from source to destination. The second is forwarding. Okay. One term that we used here is routing in the above one. Now we are using forwarding. So I would mention here routing. There is a difference between routing and forwarding. Let's first understand what routing is. I need to send a packet from source to destination, like in this picture. I need to send the packet from A this is the source to the destination, that is here. How I will send it? I would use some routing protocol, and the routing protocol would help me in finding the path. What would be the path? Whether it's shortest and so on, it will find a way through this and make me reach the destination that is shown here in yellow color. Fine. As compared to this, I mean, this is what we have as overall network-wide process routing, and it's end-to-end path from source to destination. Compared to this, what is forwarding? Forwarding is a router local action. For that, I would use another color, let's say a red color. When the packet arrives here, it is to be forwarded to the link that is on this side. So passing this from here to this within a router. So passing off the packet from here to here is a local action, a router local action. It transfers from an input link. So let's say if this is our input link, passes on to the output link. How? Within the router itself there is a forwarding table that helps us in doing this. So forwarding refers to a router local action of transferring a datagram from an input link interface to the appropriate output link. Compare this to the routing part, overall network-wide process that determines end-to-end path. Fine. This is what we have about the difference between the two. Now moving on to the next one. Is for this is forwarding, the second thing that it does. So in forwarding, when a packet arrives at the input of the router must check what the destination, and it must decide where to move it, and it will move it to the appropriate output link. The third part is call setup. And what is there in call setup? Certain network layer architectures like ATM. The example here is ATM, not the one which we do which we studied previously. The ATM architecture, it requires that the sender chooses a path from source to the destination. How? We understood this, if you remember, the call setup, if you remember the virtual circuit. If you remember virtual circuit, there was, you know, a communication between sender and destination in which they decided that all packets must pass through the specific path. Then we discussed that there were virtual circuit numbers, right? Each router had that table which would pass based on that. We did not use source and destination IP address. But the important aspect that we did is that all the packets would pass through that virtual circuit. Since all the packets has to pass through that virtual circuit, this also means that first you need to establish this virtual circuit. ATM is an example of the devices, the network that uses virtual circuits. Network layer here is responsible of doing this setup. There can be an interesting question that can be asked in an exam, wherein we'll say that the next layer that we are going to study is transport layer. We can say in transport layer there is a three-way handshake. The sender and the receiver decides to set up, the connection between the two. So it's a connection oriented service that we say there. But there is some connection oriented service in network layer also. So I can ask you, what is the difference between the connection, the oriented service of network layer as compared to the connection oriented service of transport layer? So if a question like that comes, you should keep in mind that network transport layers connection oriented service is about TCP, that is the three-way handshake, which we are going to study. And the network layers connection oriented service is the ATM architecture, in which a virtual circuit is created, in which call setup has to happen. Source and the destination does handshake with each other in order to set up this virtual circuit link. And once this virtual circuit is done, once this call setup is done, then only all the packets would pass through it. However, network layer of internet, it does not perform such call setup. Okay, so these are the three important functions that we see in the network layer. So what does network service model tell us? There are two aspects of network layer here. One is known as data plane, another is known as the control plane. What is the data plane? If you're talking about local, router local function, it's about the data plane. Control plane, it's a network wide logic. Like I said, end to end, like routing, end to end sending and sending to sender to the destination between the two hosts. But within this, that is control plane. And within the router, we would talk about data plane. Forwarding is about the data plane. Routing is about the control plane. This we just now discussed. So what is the network service model? Certain questions that we need to answer, which can be answered by the network layer, such as I have to do the packet delivery to the destination. What path am I going to take? What about the multiple packets that I am sending? What about the time I will take? How much delay I would have? What about the congestion and so on? All these questions would be answered by our network layer. An example here, the slide is given. Is it guaranteed delivery? Guaranteed for how much delay? And so on. Whether the delivery would be in order or it would be out of order. If I'm talking about in order delivery, I'm talking about virtual circuits like ATM service. Internet typically would expect an out of order delivery. This we discussed when we were discussing about virtual circuits. So all these abstractions are provided by the network layer to the upper layer. Whether you are using virtual circuits or not, whether it's in order or not, whether there is a guaranteed delivery or not, whether there is a guarantee of minimum bandwidth or not, whether there is feedback about congestion and things like that. This abstraction is done by the network service model for the higher layer protocols. So here we have a comparison, a good table in which you would understand the network architectures. There is about internet, there is about ATM services, there is CBR, VBR, UR, where it stands for constant bit rate, variable bit rate, and arbitrary bit rate. And the service model of internet is best effort. We had also discussed this previously. And there is a comparison given. You should go through it and understand what guarantees are provided. Okay, is there a guarantee of rate? Is there a guarantee of loss? Is there a guarantee of order? Is there a guarantee of timing? Remember the example of the best effort service I gave? Uh, Anybody who remembers? What example I gave for best effort? Internet's best effort mode. The example was about your friend who would, whom if you give money and say, I'll try my best, but I can't guarantee whether I can give you back. And also I cannot guarantee that I can give you on time or not. That's why the first thing that you see in the network layer service model here about the internet here, it's none, no, 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 and no. So internet is a best service model. It does not guarantee any bandwidths. It does not guarantee that there won't be losses. It does not guarantee that there will be in order delivery. It does not guarantee you about the timings, and also it does not guarantee about feedback congestion. Then what happens in these cases if we have packet loss and not in order delivery and things like that? We have other protocols also which take care of it. If we need a guaranteed delivery, we would use a higher layer, transport layer protocol, which takes care of this. Okay, I'll give you some work to do. I'll just send that separately about, router's architecture, how our router looks like. And also I'll tell you to discuss about the CBR, ABR, and so on. So as of now, I hope you understand these things and you understand what I just now mentioned, that there can be connection oriented between network as well as transport layer. Network layer is about virtual circuits, circuit setup, and transport layer is three-way handshake. We also discussed that routers are the intermediate nodes which understand this. If we have switches and other devices, they are oblivious to what is happening in the network layer. Any questions till now? No? No questions? Any questions? Okay. If that's it, so I'll end my class here. We'll start with the routing protocols in our next class. So we discuss about the assignments. We have meeting also, and we'll see how we'll go about the rest of the assignments. So as of now, to end today's class, the network layer has specific functions that we understand. Some functions that were given here, which I just mentioned here one by one. One is the path determination, which we call as routing. Then we have call setup also. In addition to that, there is addressing. What is addressing? Network layer gives its own addressing, which we call as IP address. Okay, we are going to discuss this as well. And there is some sort of error reporting that network layer does. For example, we say ICMP. Well, some books would say that it's a high layer protocol. There are transport layer protocol which uses the network layer protocols for transmission. Anyhow, we'll discuss that as well. So these are the functions that we are going to discuss. I'll end it here. All right. Ramanand, any questions? All right. All right. Thank you. Hope to see you next class. Bye.